I'll hit record. Hello, everybody. Welcome back. Thanks for being here. Happy Thursday. I have in front of us, let me get the screen share going so we can all be in front of us, the course syllabus. Wanted to let you know that I have, in addition to your next formative assessment that is due on Monday, I have put up your next homework, except I pushed the due date back 2 days. So it will be due Wednesday, the 27th. That way I can make sure that we've covered everything that is required in it. It will go along with example 5A that we're starting today. And this one is a multivariate problem. I have it open here. You will be examining the extent to which training in making pancakes versus making crepes affects your ability to make either dish successfully. So do you know what the difference between a pancake and a crepe is? Thinness. So a pancake is like fluffy, and it's usually only for breakfast, or when you're having dinner as breakfast. A crepe is like a really, really thin pancake, and you can put in savory items, like potatoes and beef and stuff like that, like people make dinner crepes, or you can put in dessert type items, so like ice cream and strawberries and stuff. The latter, of course, is quite excellent. But once upon a time, back before we had children to take care of, Jonathan would sometimes make me dessert crepes as a special treat, and he got very good at making crepes. And so this homework was built out of conversations we had about whether skills that you need to make successful pancakes translate into successful crepe skills as well. So that's my story, and I'm sticking to it. I wanted to let you know that's available, although we haven't covered any of the models that will be in this homework. I wanted to get it up so that you can start working on it as soon as your schedules allowed you to. Likewise, the next formative assessment, you should be able, up to this point, to answer questions 1 and 2 by the end of the day. You should be able to answer questions 3 and 4 as well. And one more thing that I wanted to announce / show you is that a couple of you sent emails to me asking about potential errors in the homework key. And as near as I can tell for homework 4, I do have one error in question 66. So let me show you. Does anyone want to see how the homework actually gets built? Are you curious about this at all? Mm-hmm. Let me show you my SAS program. Okay. It is a giant SAS program that does everything. So this is the front end of it, where I'm defining a bunch of these are macro variables that get used throughout the program, such as which homework it is, when it's due, the number of sections, the number of points, the number of subjects. This calls a whole separate file that does a whole bunch of stuff. And then in here, I have to make individual data sets with text in them that hold all of your instructions. I then write out the individual questions, and note that I have these numbered manually with comments, which is why I had told you that when we change the order around, it changes a whole lot of things. Down here this is how we make the results section. Each time that I want to refer to a value that you've already answered, I put in a reference to where it is in the database, and it's stored by number. So like I want your answer to question 6 to be shown right here. And then this thing here activates a little program that presents the drop-down options. And so each of these has a name for which set of options I'm referring to. So we go through this whole thing, and that's what you see. On the back end is a program that simulates your data using your random seed, your ID number is a random seed. And so then this is where knowledge about how to simulate data comes in handy, because you can simulate from all kinds of different distributions that are built into these programs. Then you have to actually run the model. I have to find where all of the results are in each individual table and store them as macro variables for each person. I have to do all the same coding that you do. So those of you who are like, my God, with the estimate statements, stop already. I feel your pain, because I do it too. And so we keep going. This is all the models. Then we code all the estimate statements for direction and significance. And then I hand enter basically the references to each type of result for each person for every single question. So these are the numeric questions. Then we get down to the tricky part, which is the results section. So all of the ones where it's like more positive, less positive, more negative, less negative, those sorts of things are built using conditional logic with the reference slope and then the interaction slope. And so like what this says is if the reference slope is positive and the interaction slope is positive, then it's more positive. And then so it has every possible combination of the four. And so what had happened is here's question 66. The pattern on this part was supposed to be 1, 1, 2, 2 like all the others, and for whatever reason I wrote 1, 2, 1, 2. So that switch of two individual numbers is what created the homework error. And I'll point out that this happened on lines 607 and 608 of this program. So it's kind of a miracle that I don't screw this up more often. So this is to say, it's entirely possible that I've made a mistake when I set these things up. I go through and I do my own homework, and I do it in all three programs, in part to make sure that my coding is correct. But if you do see something that you think is incorrect, please let me know, because it is possible. What's interesting is that I gave this homework 2 years ago and no one said a word. So either it worked out that no one had an incorrect answer by accident, or they just were, so demoralized by question 66 that they didn't want to tell me about it. But anywho, this is the thing that is going to become an actual program, as opposed to a very, very long and kludgy SAS file, which is what I know how to do, because I'm not a programmer. So I will fix homework 4, question 66. I'm waiting until to make sure that there's no interference with the people who are still working on the assignment. So I will eventually fix it, but I'm very nervous anytime I have to go into the databases and mess with anything that I will screw it up. So I'm waiting until more people are finished with that, but it will be coming. Okay, I think that's all the logistics announcement stuff. So recapping, your next formative assessment due Monday. Your next homework is available. You won't have all of it be able to be done yet, but I wanted to make it available so you could get started as soon as you wanted to. And I'm looking at the 3 weeks that we have left. Can you believe it's only 3 weeks?
What?
Yeah, 3 weeks of classes, 4 weeks in total if you count finals week. And I'm looking at all the things that I have left and thinking we're going to run out of time. So there may be some things that I don't end up including. In particular, I think example 5B is going to have to go, because that one is peripheral relative to the others. But anything that I don't put up for this year, I will put up links to where I had talked about it previously so that you would still have access to those materials. And just as a heads up, during finals week, there will be no class, because we don't have classes on finals week, and there will be no final. You just have to finish your last homework, just like normal. And it's worth like 17 or 18 points, like enough points to where you can't skip it. Because I've had people do that before, like they earn enough points to get like a B and they're like, I'm done. So there's no way that you can get a B without doing the last homework. I do, however, plan to have office hours during the times that I would be teaching. So Tuesday and Thursday of this week, I'll be on Zoom office hours from 12:30 to 4:30. And that way anybody who is behind or otherwise wants to spend extra time working with me on this will have opportunities to do so. And if you finish your last homework before finals week, you're done. So it's up to you how quickly you want to check this class off your to-do list for the semester. All right, any questions on logistics or anything else I can help you with? No, everybody knows what they're supposed to be doing? Cool. Then I'm going to shut this down. I'm going to pick up lecture 5. So in the interest of making sure that we cover what you need for your homework, I am going to skip a section of this and pick it up later. We were talking last time about ways of modeling dependency. And what we had covered thus far is the direct way of doing it, the idea of letting the residuals from the same person be correlated within an R matrix. So this was slide 16 here. So the big difference in terms of the software with the multivariate aspect is that we have to tell it that we want each outcome to potentially to have a different residual variance or to share residual variances across outcomes, and then whether we want each pair of outcomes to have a residual correlation or to share a residual correlation across pairs. So the safest and best option is to fit what's known as unstructured, which is what the first example does, and that's what your homework's going to do too, because your homework only has 2 outcomes, and the first example only has 3. And that's just letting the data do whatever you want. So we'll sort of set that aside for now so that we can focus on what happens to the model for the fixed effects. How is it that we can predict multiple outcomes simultaneously when all the outcomes are stacked into one column? So I want to show you the parameterization of that and options for how to do so, because knowing how these pieces work together can help you figure out which version is going to be most useful to you for a given task. So I want to start here, slide 27, skipping ahead a little bit over the indirect random intercept section, which is not immediately relevant to us. All right, so we'll pick up there. So there are 2 different ways in terms of how you set up the fixed effects that I want to explain to you, and they tie to how you're thinking about the multivariate aspect of your data. So if the situation that you're in terms of your analysis is a traditional repeated measures type design. So I have data from somebody from condition A, they were in condition B, and then when they were in condition C, and I'm interested in seeing differences in performance across those 3 conditions. In that type of strategy, where what you're trying to do is look at mean differences across conditions as well as potential moderation of those mean differences, those are within subjects or within person comparisons. A strategy that uses a general intercept is probably going to be most useful to you. And this is what we've done up to this point. So a general intercept means a column of ones that applies to every single case as part of their prediction. So the beta 0 that shows up at the beginning of the equation. We have taken for granted the fact that we want one of those. In some situations, you actually don't. So if you're in this sort of traditional thinking about condition mean differences as another predictor for you, having a general intercept like normal is going to be useful. If you are interested instead in thinking about outcomes as sort of separate conceptual things, so like I'm predicting, in the example that we're going to have, I'm going to be predicting answers to the same questionnaire from the dad of the family, the mom of the family, and an adult child of the family. Like I'm thinking of those as 3 separate outcomes that I want to predict simultaneously. In actor-partner kinds of things, these would be known as actor effects if you have a predictor for oneself on one's outcome. Partner effects if you have like your predictor on your partner's outcome instead. So for that sort of situation where it's not really conditions so much as just logically separate outcomes, it can be more useful to specify what I call dependent variable specific intercepts. So this strategy allows us to shut off the general intercept and instead make separate versions of it that pertain to each separate outcome. Then what you end up with is each outcome has its own set of predictors in the model, and it corresponds directly to how the setup works in path analysis as well.
I have a question about that.
Please.
So is that going back to the balanced and unbalanced idea?
Yes.
Okay. So that would be an unbalanced example.
Balance and unbalance is a little bit different. So these would both be under the balance case.
Okay.
Yeah, because we're not dealing with unbalance in this class. You got to come to a different class for that.
Yeah. So because they still have the same opportunity to choose, they just maybe don't. They don't. There's a different number of what they choose in the end. Is that the way to think about it?
Balance versus unbalance is whether or not there's the same possible outcomes for each sampling unit.
Okay.
So the examples that I had given, if you ask somebody to come up with 10 memories of something, each person's going to come up with an individual specific memory. Memory 1 is not going to be the same across all the people. Whereas if you give someone a 10-item test and everybody gets the same items, item 1 is the same across people.
Okay.
So it's actually like a cross design rather than a nested design. Likewise, if you had, pre-test, post-test, and follow-up is 3 longitudinal occasions, and those all happened at the same time for everybody. That's balanced. Whereas if I had something like answer the question in the morning and answer the question in the afternoon and answer the question at night, if those aren't at the exact same time, then they're unbalanced, because then there's a different potential set of times for each person. Okay, does that help? Okay, your question.
Yeah, I have, well, 2 things. First, can you repeat what is the DV specific intercept advantages? And
So the advantage is that then what you get out of the model directly are the effects per outcome and not the differences across outcomes. So I've got examples of this to show you what I mean. But DV stands for dependent variable.
okay. And the other thing is, how is this related to the indirect and direct?
It is
multivariate?
completely separate.
Okay.
So the direct versus indirect is about how you build in the residual correlation for outcomes from the same person. In direct, you can just let it be there. So you have an R matrix of residual variances, and you can allow those residual variances, you can allow covariances for the residuals that show up in the R matrix. Let me say it correctly. The indirect way involves adding random effects to the model that induce a correlation such that the E residuals remain independent.
Okay.
And so that's a variance thing. So I'm setting that aside for today and saying we're just going to use unstructured, and moving on to how are we going to set up the fixed effects in the model given that we're predicting multiple outcomes simultaneously. So that's what, this is that, the latter. Okay, other questions? All right. So in the situation where you are hypothesizing different effects of the same predictor across outcomes, here's why we need to do this in a multivariate model. So let's say you didn't know how to do a multivariate analysis and you had a question about whether or not your treatment was more effective for anxiety than it was for depression, something like that. So we'll call these A and B. So I may have, this is an effect size continuum here that I'm trying to describe, and here's the arbitrary line in the sand at which P is less than 0.05. So anything that is on the right-hand side of this continuum would be considered significant, and anything on the left-hand side would be considered non-significant. And where this line in the sand gets drawn is a function of your sample size. The more people you have, the further to the left it goes. The easier it is to find small effects to be significant. The fewer people you have, the more to the right it goes. So in this case, it looks like I would come to the conclusion that I have a significant effect for outcome B and outcome A. Now, does that mean that it's the same? Not necessarily. Just because you have one model that has a significant predictor of outcome A and you have a separate model that has a significant predictor of outcome B, you can't make any kind of statements about whether or not the size of that effect is the same across outcomes. In order to do that, they have to be in the same model. Likewise, what about this situation? Let's say that you have an effect that's just non-significant for A, but it crosses the arbitrary line in the sand for B. Would you come to the conclusion that the effect is different across outcomes? You can't judge it based on significance alone. We need a comparison of the effect size. So the question is, which of these do you care about more? If you stick with a general intercept, you're always going to get the green part. If you stick with DV-specific intercepts, you're not going to get the green part. That's going to have to be a linear combination, but then you'll figure out what happens for both A and B as a function of the model fixed effects. So this is another situation in which, like for 2 outcomes, the model is going to give you 2 pieces of information, and the third is a linear combination that you can ask for. But it's up to you which 2 you get directly. So let me show you how this works. The 2 different ways of fitting fixed effects in this sort of multivariate situation. So I have a stacked data set. Do you remember that from last time? Each person's data stacked into a single column. So you have 1 row per outcome per person in a stacked data set or a long data set. And so we have DV is a categorical indicator variable that keeps track of whether I'm talking about outcome A, B, or C. I've got 3 here for the sake of illustration. And a general intercept would be a single column of 1s. If we keep that in the model, a person level predictor X, so that would be something that is constant to a person across their 3 outcomes, and 3 dummy-coded predictors that differentiate each outcome from the others. So the code to set up these 3 dummy codes would look like this, where if it's DVA, for instance, that dummy code gets a 1 and 0 otherwise. If it's DVB, that one turns on, and so forth. So these DVA, B, and C are redundant with this first variable, but they get used in separate places in the code. So the fixed effects are going to have the dummy codes. The R matrix for the residual variances and covariances is going to be structured by this DV variable instead. So we can have a general intercept, or we can have DV-specific intercepts, is our true strategies. If we keep the general intercept, then one of our DVs is going to be the reference. And the fixed effects for the others are going to give us the difference between DVs, the mean difference across them. If we do that, then any of the fixed effects for the slopes for the non-reference DVs are going to have to be found as linear combinations. The other way of doing it is if we give each dependent variable its own intercept and shut off the general intercept, then what we get is what happened for each outcome in the model directly. And if we wanted to know about any differences in the fixed effects across outcomes, those are found as linear combinations. And this is how path analysis works, the second way. So let me be a little more concrete. No, not yet. Less concrete, then more concrete, I promise. I've got a goal in mind. So factor variables, I have deliberately avoided in both of my classes this semester because it's yet another way that programs differ from each other, and I'm trying to minimize that. But for those of you who have used factor variables before, what I'm talking about is in SAS, if you put a predictor on the class statement. In Stata, if you use I dot as a prefix rather than C dot, it's called a factor variable in R. In SPSS syntax, it's the by line instead of the with line. Every program that I know of has a way to do this with the exception of M+. It is the only one I know of that does not have something for this built in. And when you invoke this option, it creates that same set of dummy codes that I just demonstrated here for you internally automatically. So when you put in DV as a predictor in the model, you're also adding these things internally without you having to actually make them and write them. It differs by package, which is the reference category. So in SAS, for instance, the highest category numerically or the last alphabetically is the reference. In Stata and R, the lowest or the first category is the reference, and you can change this around. In SAS, you can't, oddly. It's one of the things that seems to be locked in. Changing it around leads to internal inconsistencies in the code, so I wouldn't recommend that. But under this version of telling it about what your DV is, it decides how many of these dummy codes go into the model. So if you keep the general intercept, it only needs 2, because otherwise the third is redundant. So if I have 3 potential outcome variables, I need 3 intercepts. If I keep a general intercept, I only need 2 more. If I kick out the general intercept, then I need all 3 of these. And so when you let the program do this sort of dummy coding for you, everywhere that you refer to the factor variable, you'll have to tell it what to do with each of these internal variables. So that's part of the reason why I've shied away from this. I wanted to introduce this here because it can make it a lot faster and easier to specify multivariate models if you rely on this sort of internal coding representation. So here's what I mean by general intercept. This is the way that you're used to seeing a linear model be built. So I have y hat, which is 1 column, remember. All the outcomes are stacked into 1 column, and I've got outcomes A, B, and C here. So outcome for individual I and DV, D, that's the D part here. This looks like a model that has 2 predictors in it. Would you agree? I've got 2 things that look like slopes here. No?
No.
I can't trick you, can I? I would call this an empty model still. even though that what looks like two slopes here, because what these slopes are doing is differentiating which dv is which. So this is how we end up with separate intercepts to start off our linear model prediction for each outcome variable. So beta 0, because we have dVA and dVB here as predictors, that means it's going to be for the reference outcome, the one that's missing. So the general intercept becomes the expected intercept for dVC specifically, because that's when these two dummy codes are coded 0. Beta 01 and 02, because they pertain to outcome, that's why it's an 01 and 02, they hold the mean differences for how each of the other outcomes differs from C as a reference. So we directly get the intercept for C. We directly get how the intercept for A differs from the intercept for C. And we directly get how the intercept for B differs from the intercept for C. That means that if we want to know how A and B differ from each other, that's a linear combination. And if we want to know what the intercept actually is for the non-reference outcomes, that's a linear combination. So it takes the general intercept plus the effect of A to get to what the intercept is for A, the general intercept plus the effect of B to what it is for B. Okay, so this is like the dummy coding that you're used to seeing for predictors. But keep in mind, these aren't really predictors. They are indicator variables indicating which outcome is which. So it might be a semantic distinction, but it's a little bit different to me. Ding dong. Okay, questions so far? Yes?
No, that's in the next.
In the next one?
Outcome specific.
Yep, yeah, we're not there yet.
No.
Yep. So if I have a repeated measures study where the point of the study is to see how people perform differentially across outcomes A, B, and C, this tells me that directly. Beta 01 is going to hold the difference between condition how A differs from C. Beta 2 holds the difference. So then any research questions about how within-person differences across A, B, and C are moderated by blah, 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 this is directly going to tell you that. So for instance, if I add a person predictor X, let's say that this is a person's background characteristic of some kind, that way it would hold equally across all three outcomes. So it's a person between person characteristic. If I put in, so I'm keeping what's in the model right here and adding to it. I'm adding in what looks like a main effect of X, what looks like an interaction between X and dVA, and what looks like an interaction between X and dVB. So those new terms then, the main effect of X is specifically for dVC, because that's the only time when these ones fall out. Beta 11 is how the effect of X differs between C and A. And beta 12 is how the effect of X differs between C and B. And then we have three linear combinations potentially of interest. We have the difference in the X slope for the non-reference outcomes, as well as what the X slope actually is. So this model would tell you if the effect of X is significant for outcome C. It would tell you if the effect of X differs for outcome A, and if the effect of X differs for outcome B. But it does not directly tell you if B has a significant effect of X and if A has a significant effect of X. Those are linear combinations you'd have to ask for. So everything in this parameterization is set up to give you a given set of effects for the reference dV and how those effects differ for the other dVs. If that's what you want, Godspeed. But if what you actually want to know is, how does X predict A? How does X predict B? How does X predict C? This is not what you want. You want the dV-specific intercepts instead. Okay. How are we doing? Thumb sideways. Yeah, I in my other class, I told them that whoever's listening, because everyone's listening right on the internet, whoever's listening who works at Zoom, can you please give me a thumbs sideways emoji and a thumbs down emoji to add to the list? Thumbs sideways is like so-so. We use that at our house all the time. And I nominated thumbs down as the poop emoji. You can use that one to indicate thumbs down. Andrea has her hand up.
Yeah, thanks. I'm just wanting to make sure I understand this. So if we were trying to, on the bottom there, if we're trying to get the xi slope for either A or B, we don't add like the beta 0, 0
Nope.
intercept for C in that case?
Nope, because we're talking about the slope of x, not the intercept.
Oh, okay. Thanks.
Yep. Same rules apply if you want to talk about how do I build a simple slope. Only the terms in the model that have the slope are relevant. So none of these three terms would be relevant if I want to talk about the effect of x, because x is not in there. Yep. So the same rules apply that you're used to. What this would look like in software, I've got all three packages in here as a generic example. So given that DVC is the reference, the way that I would build my fixed effects would be to include DVA and DVB as main effects. Those give me the differences in intercept relative to outcome C as the reference. The main effect of X by itself, which becomes the effect for DVC specifically, and then DVA by X and DVB by X. And that would give me the difference in the effect of X for these conditions instead. And in Stata, it looks the same way, except for the use of C dot and the hashtags instead. And this is something, I don't know if you've seen this yet. You may have, but I don't remember if you have or not, but I'll do it again. And this is how we tell the nesting structure in mixed. So person ID is the person level identification variable. And in mixed, it defaults to include a random intercept for it. We don't want that. So that's what this no constant does right here, is shut off the default random intercept that you get in Stata. There is no such default in SAS. So there's going to be a new command we haven't seen yet called repeated that controls the structure of the R matrix. And so that's why I have the question marks here, is because that's up to you what kind you want. It can be unstructured, it could be compound symmetry. You would do a likelihood ratio test to figure out which one fits relatively best. So if I did all of the coding myself, it would look like this. If I used the class statement, or I dot, it would look like this instead. So here I have DV rather than the two specific dummy codes. And because DV is on the class statement, it understands that when I refer to that, what I want are separate contrasts for each potential DV, treating it as if it's a categorical predictor. So then I only have to list one term instead of two. DV takes care of the A and B dummy code versions. And in Stata, it's the I dot, and I've changed it so that the reference is last to match what it would be in SAS. So both of these specifications would end up with the same result. One has more control, one has less typing. And R, folks, I didn't forget about you. So we're using GLS still because that's the only way that I can find to estimate models with a residual maximum likelihood and not have random intercepts. So we have the single column Y is predicted by the 1 is still here for the general intercept. I've got my DVA and DVB dummy codes, my main effect of X, and my X by DVA and DVB interactions. Or I could just say, can you make this a factor? Cool. And I made a new variable DV3 where the last category is the reference to match what the SAS output would be. And so these two pieces here, correlation and weights, are how you control the R matrix. And I'll give you code for that here in the example that we're following. Okay. So this is what I would recommend if you're in a repeated measure situation where what you want to know are differences across within subjects' conditions and how those differences are moderated by person-level information. I would also recommend this if you're interested in different scores. So if you want to do something like how people change between time 1 and time 2. If you have a general intercept, and if you make that the reference for time 1, then a dummy code differentiating which occasion is which directly holds the change between 1 and 2, and you can see how that varies as a function of other predictor variables. Okay, Questions? Yes, go ahead.
So they're not predictors, but they're in the location where predictors would normally be.
Mm-hmm.
So
Mathematically, they are predictors, but
Okay.
conceptually, I think of them as identification variables to switch from talking about what happens to DVC to what happens differently for DVA and DVB.
isn't that kind of ANCOVA in a way?
Yeah, I mean, this is what a repeated measures ANOVA would look like under the hood if you ran it as a linear model. So it's the X is a predictor.
Okay.
So X gets a fixed slope. The use of DVA and DVB here is to control which rows are getting predicted by which fixed effects. And so, like, we're not talking about C anymore for anything that has DVA or DVB as a component to it. They're switching you from a different row of your stacked outcome. Okay, other questions? All right, now here's the alternative. And you're either going to love this or hate it. I actually love it. This is what I do. So the DV-specific intercepts version takes out the general intercept. It shuts off the beta 0 that all of these programs give you by default. And we do have to add that to the code. So there are no terms in here that are not attached to a DV dummy code. The DV dummy codes directly control what fixed effects predict that row. So what I used to call beta 0 is now being multiplied by DVC so that this is specific to DVC. So that means that in the SAS data set, or whichever data set you're in, this parameter would only contribute to a predicted outcome if DVC equals 1, meaning it's for that row where DVC is. Otherwise, it doesn't contribute. Likewise, beta 0, 1, this is not a difference. This is the intercept for DVA. Because there's nothing that it's relative to. Because I don't have a general intercept that applies to everything in this case. I have specific intercepts that go with each outcome separately. So beta 0, 1 is going to tell me what the intercept would be for DVA, and beta 0, 2 is going to tell me what the intercept is for DVB. So then any differences are linear combinations. But I directly get what the intercept is for each outcome. This is how it works in path analysis. Each outcome is a separate box. It has its own intercept, it has its own residual variance, and it will have its own slopes. So if I add a predictor, the same predictor X, I've underlined where it's different. There's no main effect of X here. X is never by itself. It is always attached to one of the dummy codes. So then this beta 1, 0 tells me what the slope of X is for DVC specifically. Beta 1, 1 tells me what the slope is for DVA specifically. And 1, 2 tells me what it is for DVB specifically. And I'm looking here and seeing typos. Fix these to be ID, would you? This is what happens when I go back and forth across my notation and change my mind. I don't always catch it everywhere, but this should be ID to be internally consistent. Question?
So is this like combining submodels together in a way?
Yeah.
Okay.
Yeah, that would be a good way to think about it, is that I've got 3 submodels going here to predict my general Y outcome. And these are acting like light switches that only turn on that parameter if you're in that row. So then this directly tells me what the effect of my predictor is per outcome, and the differences in those slopes are linear combinations. So in your next homework, this is the type of strategy I recommend. So what it looks like in code is the addition of no int as an option on model in SAS, and a second no constant in Stata. And no, this is not a typo. The no constant that shows up before the random part is shutting off the fixed intercept. The no constant that was showing up before after the random part is shutting off the random intercept. So I'm writing out all 3 dummy codes and attaching the slope of x to each of them. So there's 6 fixed effects in total, but conceptually what I have for each outcome is 1 intercept and 1 x slope. The shorter way to do the code is to use dv as a factor variable. And without the intercept, then it uses all 3 internal columns, and it does the exact same thing as writing out them 3 times would do. And in R, it would look like this. So these accomplish the exact same thing. The top way is more flexible, the bottom way is faster. So for instance, why would you want to do it the top way and write out more code? What if you didn't want all slopes to go with all dv's? Let's say that x isn't relevant in predicting dvc. All I would need to do to make x not predict dvc is take this one out. And then x doesn't predict dvc. It's harder to figure out how to do that when all of the dv's are bundled together in a factor variable. So it is possible, by the way, to mix and match across general and specific intercept versions. You can do whatever you want, but you just need to be really careful that you know what you're doing. So for instance, here is a model where I have 2 predictors, x1 and x2, and I have the general intercept version and I have the dv specific intercept version. So here, under general intercept, I have beta 0 that applies to all outcomes. That means that beta 1 and 2 here are going to create differences of that reference outcome for relative to the reference for A and B. Likewise, this one is going to be specific to C, and these create differences. Now, the last line here, because we're following the same pattern for x1 and x2, you would be inclined to think that these represent differences, but they don't, because there's no main effect of x2 here. So that means that with respect to x2, this functions like its specific intercept version, where this would be the slope for x2 for A, this would be the slope for x2 for B. So in your homework, for instance, there is 1 predictor variable for whether a participant was trained in pancakes or crepes, and each person makes both dishes. So there's like a congruent, incongruent 2x2 crossing that's happening. And I will tell you, when I wrote the solution for this, I created 4 intercepts. I gave each combination their own intercept so that I could get the differences across them as linear combinations directly without having to figure out main effects and differences. So you can set this up however you want. It's just a question of what is going to be most useful. All right, how are we doing? Thumb sideways is my only goal right now. That's the most I can hope for, is sideways. Want to see some numbers? Numbers usually help, I think. Usually. Not always, but usually. Okay. Let's look at some numbers here. In example 5A, new one. Make sure I'm recording. Yes, I am. Good deal. So these are real data. These are data that I borrowed from people while I was at Penn State as a postdoc. And I have, so in that department where I was working, it was human development and family studies. So there were a lot of research studies that people were doing where they collected multiple observations on the same family. And this one in particular was looking at gender roles and attitudes about conservative gender roles with respect to what girls should do and what moms should do and that kind of thing. And so the setup here is that they found intact families of 2 parents with an adult child. So there's a mom, a dad, and an adult child that's either a boy or a girl. That's the setup here. So I have 140 such families who participated in this study. Each of them answered the same questions with respect to their beliefs about gender roles in a marriage, which is a set of items measuring that. And so the outcome variable is the average across items. So it ranges from 1 to 4, which was the Likert scale that these were on. And for those of you who are saying, why isn't this an SEM if I'm adding items together? Because that's not this class. That's how I would have done it in the fall, but we got to work our way there. So we're just doing observed outcomes for now because this is complicated enough. So I only have 2 predictors. The gender of the adult child, which should, in theory, potentially matter for their own attitudes, but not necessarily matter for the attitudes of the mother and the father, because we don't know how many other siblings the adult child has, as well as the years of education of each family member, centered such that 0 equals a high school degree. That's what we're looking at here. So I would hypothesize that people with less education might have more conservative gender attitudes. So we are using residual maximum likelihood. We are using, denominator degrees of freedom is a thing. So this is one instance in which what I had to do for the handout is going to be a little bit different than the instructions for your homework. In this handout, I am using a method of computing denominator degrees of freedom that's known as Satterthwaite. So in these sorts of multivariate designs where you have potentially missing data, it's not necessarily obvious what your degrees of freedom should be for the sample. You can think about it being pertaining to predictors at each level. So like person level predictors should probably have denominator degrees of freedom that resemble number of people, whereas outcome specific multivariate level predictors should probably have something that's closer to the total sample size. Satterthwaite is one of the methods that is most recommended. And so I did that because of that in SAS and in Stata. However, R, of course, does not play nice. R threw up at me when I tried to ask for Satterthwaite degrees of freedom. So in your homework, I asked you to switch to a method that is residual, which is what R does, so that you could get the same answers across programs. So in this case, I'm dealing with an outcome that is bounded. It's bounded between 1 and 4, which is the average of the items that went into the outcome variable. So part of this is going to be just demonstrating multivariate stuff, but the end of this handout is going to be addressing, hey, are you sure that normal is a good distribution for this? Because isn't this a generalized linear modeling class? So I'm coming back to that. But the purpose at this point is just to show you how the fixed effects get set up and how you get your data in the right shape to be able to do this in the first place. So we start with a data set that looks like this. This is the wide format where each family is stored on a different row. So I've got the gender of the adult child, the education level of the child, the mother, and the dad. So this would be a family where each of them had 2 years of college, it looks like. And then the kid's gender attitudes. The kid is not conservative at all. The mom is a little bit conservative, and the dad is not conservative at all. So we have to take this and convert it into a long data set where it's 1 row per outcome, which in this context is family member. So at the end of the code I'm about to show you, this is what the data set's going to look like instead. So the original variables are at the front here, and I'm going to be adding a variable that's dv, which is being treated as a categorical predictor to which I added labels. I'm going to cheat in R and make it a string. I have 3 dummy codes for which dv is which. So this is like dva, dvb, dvc. And then I have marital attitudes for all 3 people stacked into 1 column. So this is 2 families worth of data in this snippet, 2 rows to 6 rows. That's what's going to happen in the code. When the second half of this handout shows the same models via path analysis, it will be using this original version of the data instead. Okay, ready to see the stacking? It's not so bad. So in SAS, first off, I am importing a SAS data set directly, and I am writing 3 lines of data. So the key part of this is the word output. That means take all the data and write it to a new line. So this is going to essentially make 3 copies of the data set, like all stacked on top of each other. So I'm creating new columns. Note that the word that is before the equal sign stays the same across these 3 lines, and what changes is what goes into it each time. So DV, I guess I did cheat and make it a string here too. I do this sometimes when I'm feeling lazy. So I have a categorical variable for which DV is which. I've got my 3 dummy codes, and then I have 1 outcome that's going to be called marital that's going to hold all 3 of the individual people's outcomes. And then I labeled it. So if you had more data to be included, you would add additional commands for each person. And then I am subsetting the data to only families that have everything I'm eventually going to have in the model so that the cases stay the same across the analysis. So you will get a chance to practice this on homework 5. So any questions on SAS code so far? Okay, Stata code. So Stata has a thing that I found to do this relatively painlessly, and it's called Reshape. The only catch is that your variables have to be named a certain way for this to work. So after fighting with Stata to try and get around that restriction, I just gave in and renamed them. So I started with variables named kid marital, mom marital, and dad marital, and I used the rename command to rename them into marital 1, 2, and 3 because that's what Stata wanted. So I'm using reshape into long. The new column that I'm creating is going to be marital, and I tells it how the rows are identified. So family ID is going to be the ID variable that holds the 3 together. And then J is the what I want the index for which row is which to be called in this case. So it would reshape like all the variables in the data set that have this kind of structure to them. Then I just had to make my new dummy code variables and my labels. So this was the only tricky part, was figuring out I had to rename everything. It wouldn't let me do it otherwise. Okay, so Stata folks, what do you think of this? All right, nobody thinks.
I use Stata when I get frustrated with R.
Oh, I'm going to tell the R people you said that.
Well, you know.
You know, Stata has really grown on me. At first, I was like, what the hell is this? What are with all the commas? But it's grown on me. It's a language that is written for people who do data analysis. Like it's not a programming language. Like it's for what it's for.
And it actually has informative help files too, or like when you get an error code.
Yeah, the documentation is relatively thorough and useful too. Because again, people are paid to make it. And then we get into the Wild West of R. So I found something called Reshape. I think it might be in base R because it worked without me having to install extra packages, but it might be tied up in one of the packages. I'm honestly not for sure. But in this case, you tell it what your original data are, the direction, so whether you're going from wide to long or long to wide. The ID variable is the thing that glues the rows together. Which are the names of the variables to be stacked. So I've got my 3 versions of marital here, what the new variable is to be called, and then how I am indexing that new which row is which. So I'm creating a variable that's called DV numeric with the 1, 2, and 3. And then down below, I'm adding, making a new object of labels and then sticking it into one that's called DV so that it looks the same as in SAS, and then making the dummy codes here. Last but not least, to make the output match with respect to the factor version, I created DV3, which is a version in which dad is the reference to match the other packages. So I haven't played around with reshaping much in R. I'm not entirely sure how the code would need to be extended for more than one outcome, but I'm pretty sure that it's capable of doing that. It would have to be. In your homework, there's only one outcome to stack, though, so you can port this code and use it almost exactly. Find and replace is your best friend when doing homework, if you haven't figured that out yet. That's what I do when I do your homework. I grab my own example, and then I use find and replace until it works.
I know how to do this with tidy, but I know that's not.
If you know how to do it with tidy, then do it with tidy.
Okay.
The correct way to do R code is the way that makes it work. So beyond that, like, it doesn't matter to me how you get there. The only thing I don't want you doing is like cutting and pasting rows of data in an Excel spreadsheet or something. Just please don't ever do that. Now you laugh, but I've helped people who were doing this manually because they didn't know that you could do it in like 4 lines of code. Don't ever touch your data is the moral of the story. Don't ever touch your data. Don't ever edit it directly. Don't glue it back together with paste. There was somebody I worked with when I was a grad student, and this was someone's dissertation that I was helping with, but they were doing most of the heavy lifting because it was their dissertation. So this person did their dissertation, wrote it up, turned it in, graduated. A year or 2 later, this person wanted to publish the dissertation, and so they asked for my help, and so I went in and tried to duplicate the analyses they had reported in the dissertation, couldn't do it. Like, things that were significant were nowhere near significant. Like, it was a completely different pattern of results. And so I'm like, what the hell? So I start working back through the files, and lo and behold, at some point, the person had merged 2 data sets by pasting them together in Excel. But they were off a row, halfway down. Didn't notice. So all of the rows were off 1 relative to what they were supposed to be in the second half of the data set, and that mistake single-handedly created all of the results that were in this person's dissertation. It did not get published. So let that be a cautionary tale. Never touch your data. I also worked with grad students who were managing data, and their version of fixing errors in data was literally like opening up the SPSS data set and fixing the error, which seems fine, so long as you don't screw it up. But then guess what happened? Whoever sent the data to them were like, oh, we made these changes, here's a new data set. And guess what they get to do again? Open up the data set and make all the manual little changes everywhere. No! The correct answer is write code that makes the changes, because then when they send you yet a 3rd new version of the data set next week, you can just execute the code again and get all the changes back. Plus, you have a list of all the changes you made, should anyone need to know how you changed the original data. So, yes, so long answer to a short question. You want to pledge allegiance to the tidyverse? Godspeed. I honestly don't care. As long as you're not, like, hand entering anything. No paste button. Yeah. Yeah, I have lots of stories, and they're all true scary stories. Anywho, so I figured this out eventually. You'll get a chance to practice figuring it out as well. So here are 4 versions of the same empty model, showing you the 2x2 combination of whether there's a general intercept included and whether you let the program do the dummy coding for you or not. So I've got the code for the first 2 together because they are going to end up with the same parameterization. So in this case, I'm using dad as the reference outcome. So I'm entering in predictors according to SAS, but I think of them as switches for kid and mom. And so that's going to tell me how the intercept differs for kid instead of dad and for mom instead of dad. That means if I want to know what the actual intercept is, I need to add those back together as a linear combination. So to get to the kid intercept, it's the general intercept plus the difference for kid. To get to the mom's intercept, it's the general plus the difference for mom. And if I want to know the non-reference groups, I ask for the difference as a linear combination like usual. Or I can just say, use DV and put it here as a categorical variable. Then the code looks different because I have to refer to all three internal contrast variables anytime I want to do any kind of linear combination. The other new thing that you haven't seen before is this line, the repeated line. That controls the structure of the R matrix. So the pattern that you want for the residual variances and covariances. So you have to tell it how the multivariate observations are organized. It's by family ID as the identification variable. And then within the R matrix, which row is which is DV. So DV is being treated as an ID variable in the repeated line. It's saying which row is which. And that's important if you have missing data to keep the observations in the right slots within the matrix. So this is going to look the same throughout the entire example. I'm just using an unstructured matrix and going with it. The difference is going to be what's in the model part right here. And state of code, general intercept is being used here. So dad is going to be the reference value for that. And then we have differences for kid and mom. This is the part that shuts off the random intercepts that we don't want for this example. This is the part that allows us to have an unstructured R matrix, structured by DV, the residuals option. And then last but not least, this is how we tell it to use denominator degrees of freedom and what kind you want. So I have Satterthwaite as an option here. Satterthwaite is on right here and SAS as well. So that's the two things that will have to be changed to do your homework to match what R does, which is throw up whenever I ask for Satterthwaite. I know.
I'm laughing in solidarity of frustration.
Yeah, so what I learned last year, was it last year? Yeah, it was a year ago when I taught longitudinal, is that all of the things that I can do in mixed, I had to get like 5 different R packages to do, and not a one of them will do everything. So GLS allows me to structure an R matrix with or without a random intercept, throws up on Satterthwaite denominator degrees of freedom. Elmer allows me to have random intercepts, doesn't allow me to have any kind of R matrix, but it handles Satterthwaite degrees of freedom okay. So it's like, blah. And then IB for Stata is the let Stata do the coding for you version. And how you actually get to see your R matrices and the correlation version is with these SStat commands. So W correlation, I think, stands for within correlation. The version that has covariance after it is the variance-covariance matrix, and then the actual correlation matrix is without it. So we will get to see those things as part of the output. They are also requested in SAS right here with the letters R and R core. And then in R. Of course, I need all of this code to do the same thing. So here's my GLS call. Marital is the common outcome. Note that it's model and not formula. Why? I don't know. Because they couldn't agree. Otherwise, it looks the same. Outcome equals squiggle, and then your fixed effects in here. These two are how you tell your R matrix what kind you want. Correlation, core sim form equals squiggle ID variable for level 1, pipe ID variable for level 2. And there's no way in hell I would have figured that out had I not found an example. So parts you change what your highest level of sampling identifier is. So it's usually person ID in your homework. Today it's family ID because that's the unit of analysis. And this thing right here is which row is which in your R matrix. So it's whatever variable you made when you stack the data to indicate that. So it's DV numeric in this case. And then I think I tried the other version and it yelled at me, and that's why it's the numeric version. And then weights is the option for whether or not you want separate variances by each dV. I do not know why that's weights, because that makes 0 sense to me too, but that's what it is. So this then is the indicator for which outcome is which. So you could put number there, or this one is the string version. It took that in this case. So these are the options that are not in Elmer. Asking for log likelihood times -2 as usual. And then I had to do these extra things to get the R matrix to actually be printed. It wants to know for which person. So this was the number of the first family ID. So that's something that you would change to be the first person in your data set. And then core matrix, so this gets me what the R matrix looks like. This gets me the correlation version, and then this number tells us how many dimensions you want it. Otherwise, it prints like this huge, huge thing. All right. That's a good place to stop, I think. It's overwhelming. Question?
What if we want multiple outcomes? Then we'd have to use M plus.
Multiple, like a doubly multivariate setup?
Yes.
Your choices for how the R matrix would be structured are going to be harder. Yeah, I think at that point I'd abandon SHIP and switch to a path model.
Okay.
Yep. There's a limit to what is, like, you might be able to do it, but the amount of effort it would take may not be worth it.
Yeah.
Yeah, this is multivariate in one dimension. It is possible to have things that are doubly multivariate and triply multivariate. Yes, indeed. All right, other questions? Okay, then how about we call it a Thursday? Sound fair? Okay, well, thank you for being here. Thanks for bearing with me. And let me know if you need anything. Do your formative assessment if you can. Have a good weekend, too.
Yeah.
Yeah. Go build a snowman or some shit like that.